This is the third video, stress strain curve for mild steel. In this, topics covered are stress strain curve for mild steel, elastic limit, yield stress, ultimate stress, breaking stress. What we do here is we take a bar and tensile load P is applied here. Original length of the bar is L. Elongation of the bar after applying a tensile force is delta L. What we do is we start from 0 load and then we apply the force P1, P2, P3. Slowly we go on increasing the force P. For the load P1, corresponding stress here is sigma 1, corresponding stress is epsilon 1, corresponding elongation is delta L1. When the load is P2, corresponding stress is sigma 2, corresponding strain is epsilon 2, corresponding elongation is delta L2. Similarly, for the load P3, stress is sigma 3, strain is this epsilon 3, and elongation is delta L3. And likewise, we get the stresses sigma 1, sigma 2, sigma 3 and so on, and corresponding strain epsilon 1, epsilon 2, epsilon 3 and so on. Then what we do is on the x-axis we take the strain epsilon 1, epsilon 2, epsilon 3, and the corresponding stress sigma 1, sigma 2, sigma 3 is plotted on the y-axis, and we take the points and we draw the graph. The stress strain curve comes something like this. Now this is the stress strain curve for mild steel. What happens here is when we initially increase the load, and here in this region from the origin O up to A is a straight line. OA is a straight line. Here the material follows Hooke's law up to point A. Point A is called as limit of proportionality. Here stress is proportional to strain. If we remove the sign of proportionality, then this stress sigma is equal to capital E into strain, where this capital E is known as modulus of elasticity or Young's modulus. Its unit is Newton per mm square or Newton per meter square. This sigma here is stress and epsilon here is the strain. If we rewrite this can be written as E is equal to stress upon strain. So the modulus of elasticity E is equal to stress divided by strain. Here OA is a straight line, and if we take the slope of this straight line OA, then it is equal to modulus of elasticity E. OA is a linear region because this is a straight line. So this OA region is a linear region. Now if further the load is increased, the stress is increased, then it from A it further goes to point B. Now AB is not a straight line and the material is elastic up to point B. So the point B is called as elastic limit. Suppose stress at B is sigma E, then this is the stress at elastic limit. What is elastic limit? The material's elastic limit is the maximum stress that can arise in a material before the onset of permanent deformation. Thus the point B indicates the limit of elastic behavior. So here if the stress at B is taken as sigma E, then what happens is if the stress is less than sigma E, that means it is somewhere here, then at that point if the load is removed, then the material will come back to its original size and shape. It means that the material behaves elastically up to point B. Now if the stress in a material is further increased beyond point B and stress becomes greater than sigma E, after that if we remove the load, then whatever is the deformation change in length has taken place in the bar, it will be permanent. Even if we remove the load, the bar will not come back to its original size and shape. So the region OB is called as elastic region. So from point O up to point B is the elastic region. Up to point B, the material behaves elastically. After reaching the point B, when the load is further increased, stress starts increasing along with the strain, and it reaches a point C, which is called as upper yield point. BC is a curve. We can see here, if we increase the load further, then the stress increases and strain is also increases up to point C. BC is a curve. C is called as upper yield point, a point at which maximum load or stress is required to initiate the plastic deformation of a material. Such a point is called as upper yield point. When a metal is stressed beyond its elastic limit, it enters the plastic region. Now, when the load is increased further here after point C, the load and stress starts decreasing, but the strain keeps increasing. The curve CD is zigzag. Now we can see here from point C, the curve comes down to point D. Here the curve is zigzag, even though it is not shown zigzag. In actual, from C to D, the curve is zigzag. Here what happens is, the load increases a bit and again the load decreases a bit and again increases a bit. This happens many times till the lower point D is reached. So here it is actually zigzag. The load goes down, again goes little up, again comes down, again goes up, and like that it goes down, down, down and come to point D. And the point D is called lower yield point, a point at which minimum load or stress is required to maintain the plastic behavior of material. Such a point is called as lower yield point. After reaching the lower yield point, when the load is further increased, stress starts increasing along with the strain. So when the load is further increased from point D, we see that the load stress also increases and strain is also increasing, and it reaches to the point E. So point D to E is a curve. Stress at point E is called as ultimate stress or ultimate tensile strength. The maximum stress that a material can withstand or resist while being stretched or pulled before breaking is called as ultimate stress. So the ultimate stress is the maximum stress which the material can withstand. Here what is important to notice, the upper yield point is down and the ultimate stress is up. Sometimes what students do is they take point D and they draw the graph like this, where E is almost in line with C, or sometimes E is little lower than C. But here remember that point C and point E, if you compare, C is down and E is much up. So this is the maximum stress which the material can withstand, and point E is ultimate stress. Strain hardening region is the region between yield point to ultimate tensile strength. An increase in stress is required to produce additional plastic deformation, and the metal apparently becomes stronger and more difficult to deform in this region. So from the ultimate stress to the from the yield point to the ultimate stress, this region is known as strain hardening region, from the yield point to ultimate tensile strength. Then when the load is further increased beyond point E, stress starts increasing even though the stress starts decreasing even though the strain is increasing. Here if we further load the material beyond the ultimate stress, beyond the point E, what happens is strain is increasing. Our x-axis is strain. So in this region here, strain is increasing and y-axis is stress. So you can see that from point E it is coming down. So the stress here is coming down and strain is increasing, stress is decreasing. E to F is again a curve. Here the cross-sectional area of the specimen goes on decreasing uniformly, forming a neck, and load required for further extension decreases. At point F, material breaks, so stress at F is called as breaking stress and point F is called as breaking point. Breaking stress is a stress at which material breaks or the failure takes place. And here the material becomes strain hardening until the ultimate stress is reached. But when the necking starts to occur and the material becomes weaker again until it breaks apart. So the region between ultimate tensile strength to the breaking point is called as strain softening region, that is from E to F. So from yield point to ultimate point E is strain hardening region, and from point E to F is strain softening region. Sometimes from the ultimate stress up to the breaking stress, this region is also known as neck forming region. So this is the stress strain curve for mild steel. Here point A is limit of proportionality, B is elastic limit, C is upper yield point, D is lower yield point, E is the ultimate stress, and at F is the failure stress. OA is a straight line where Hooke's law is followed. Here stress is proportional to strain. Up to point B, O to B is the elastic region. From yield point to the ultimate stress is strain hardening region. From the ultimate stress to breaking stress is strain softening region or neck forming. So this is the stress strain curve for mild steel. Be a master. Thank you.